Okay, everybody, welcome to the event tonight for the Orange County Hadoop User Group. And thanks again to Dr. Mike Carey and Mary for the pizza setup as well. So I started this user group, for those of you who don't know, about 8 months ago with Eddie Soong. And Eddie took a job in Singapore recently, so now I'm kind of running it on my own. But we have an event today where we're going to debut Asterix DB, which UCI's ICS department's been working on for about 3.5 years now, so it's pretty exciting. So we have pizza, we have Coors Light, a Chardonnay, and Coke outside, if you haven't got any already. And just wanted to introduce our sponsors, because they help us pay for all this stuff. And wanted to introduce PSSC Labs. So this is Eric Lesser from PSSC Labs, and he'll go ahead and introduce his company based in Lake Forest.
Thank you. Actually, it's quite interesting that we have beer and wine on a Thursday night at university towards the end of the year. I remember when I was in college, we were crazy. We'd start our weekends on Tuesday or Wednesday, and we didn't have enough money for Coors Light. We were buying Milwaukee's Best. So good for you guys that we can enjoy something nice, nice refreshing beverage. PSSC Labs is a hardware supplier for servers and Hadoop clusters. And we've been in business since 1988. All of our systems are assembled here in Southern California. We're all supported here in Southern California, and we've deployed our...
Let me let you talk in this, because in the back they can't hear you.
Okay. And we've deployed our systems all over the world. So we've been a sponsor of Orange County Meetup Hub for since the very first event, and you know, we're happy to continue to support this community. I do want to announce that on Tuesday of this month, which is the 25th at 11 a.m. Pacific time, we're going to be doing a webinar to cover a couple of topics, probably of most importance to you guys. The topics are optimizing the cluster hardware and software configuration for Hadoop and big data analytics, and also the cost analysis of owning a Hadoop on premises versus using the cloud as a Hadoop resource. So we're going to be sending out some reminders for this, and you'll see some emails as well as posts on the meetup group. But anyhow, thanks again, and enjoy the beverages tonight.
Yeah, so in regards to the webinar, I'm going to send an email out tomorrow, a mass email, and it will give the link to where you can register for the webinar for PSSC Labs. So it's free if you're a member of Orange County Hadoop User Group. And to get on the mailing list, you just use an app, either iPhone app or an Android app. And the app is called Meetup. And then you just join the Orange County Hadoop User Group. And then once you join, you're on the mailing list, and you'll get emails telling you about future events, future webinars. So I wanted to introduce David Cooley from MapR.
Yeah.
And he works out of Orange County. So here, you can take the mic and tell everybody a little bit about MapR.
Sure. So we're also a sponsor of the Meetup, and MapR is a software company based in San Jose, and I am located down here in Newport Beach, work in Southern California generally, as well as points west or east, and theoretically west if we can ever find any business out in Hawaii, so wish me luck in that. So we are a software company. We produce a distribution of Hadoop that's really the most technologically advanced distribution of Hadoop. A lot of that new technology is in the file system, which underlies the Hadoop stack. Instead of HDFS, it's HDFS compatible, but it's totally rewritten from scratch to do a lot of things enterprises need, give a lot of data protection and other sorts of capabilities that you can't get with HDFS. So that's basically what we do. And I just wanted to mention, I have background in the university myself, and I'm curious how many folks here are graduate student or above at UCI or another university? Yeah, yeah. You guys have the look. I used to have the look too. I don't know if I still do. So anyway, glad to be here. Looking forward to learning about Asterix DB, and it sounds like really interesting technology, so looking forward to hearing it. Thank you.
Thanks, David. So we're going to introduce Dr. Michael Carey now, and he was one of the driving forces to make all this happen, to bring the Orange County Hadoop User Group to UCI. So we started off in conference rooms of corporations, and then we kind of grew out of these conference rooms, needed a bigger space. So I met with Dr. Carey a few months back, and he really was enthusiastic about setting up these events and wanted to give the students something extra. So I'd like to give a round of applause for Dr. Michael Carey. So come on up. So I'm going to hand it over to you now.
All right, thanks everybody for coming. So the plan is that after tonight, within a couple months, we're going to move this group into the Bren Events Center because we're going to have that many people so wanting to do big data things. So we figure we're ready here at UCI. Okay, how's that? Is that loud enough? Up higher, down lower? Higher. Start with higher here, and then we'll try higher on that. How's that? Better? Turn it up. How's that? Okay, good. All right, so thank you all for coming. This is sort of an exciting time for our group, and you can see a lot of our group is here. You look for the steel gray t-shirts. I'll talk more about those. That's our group, and so if you have questions, they'll be able to answer them for you after the talk. So I'll try to avoid all questions and defer them to the group, so you know how to find them. Just look for the t-shirt. And what I'm going to be doing today is talking about this new system we've been building, and I'll sort of give you the history, kind of first of big data from our perspective, and then also a history of this particular project, so why we did what we did, how it relates to Hadoop, which is sort of the focus of this user group, and sort of hopefully by the end you'll understand sort of what we've been up to for the last 4 years. But today is the culmination of about 4 years of work. We're basically putting this up, and we'll show you at the end where you can find it for public consumption. So we're sort of going open source as of today. It's been open source quietly for a long time, but now it's something that we're actually saying, yes, you can try this at home, and hopefully no one will be harmed. So this is the next generation system about big data management, and a couple things you should know. So first of all, we do have these t-shirts. We don't have them for everyone, but they're these cool shirts. They have sort of the Asterix DB logo here, and they have Asterix DB on the back, and you can get one, and there's a couple ways. So you can be the person who the group thinks asks the best question, sort of by the end of the talk or at the end of the talk. And so they'll sort of get together, and you might get that t-shirt. Also, I'll tell you in a second how to tweet about this if you want. And so if you're determined to have sort of given the most tweets, not just the most, but the, sort of useful tweets, you could get a shirt. Or sort of 3 lucky people who sign up in the near future on the Asterix DB users list will get selected for t-shirts. And so you can do any of those things, or all of those things actually, to try to get one of these shirts. And clearly, these are worth getting. Right? So anyway, that's where the users list is. If you go to go.google.com, AsterixDB, you can get a link from there and join the group and start hearing about what's going on as of today with this new thing. If you want to tweet about us, because that's sort of one of the ways you could get a shirt, is AsterixDB is a hashtag to use, and so we'll be watching in the back to see how things go there. Okay, so now sort of back into the more academic mode. So this is actually more of an academic talk, so I'm going to give you the context and kind of give you the perspective, at least from somebody in an ivory tower, of kind of 2 things that have been happening in parallel, slightly time shifted, about big data. So this will be like a history lesson times 2. One is kind of from 1970 to about the 2000 time frame, and the other is from like 95 to about now, and what's been going on and how they're coming together. And then I'll be telling you about sort of the main thing that we want to talk about tonight, which is Asterix DB, which is our next generation BDMS. And that's not actually a typo. It's a big data management system, not a DBMS, and we'll talk more about that. And then I'll also tell you about our software stack and how it's sort of different than the Hadoop stack, and why it's different and so on. And at the end, I'll try to convince you that we've got something that could be used for a lot of different kinds of use cases. We don't believe in one size fits all, but we do think one size kind of fits a bunch, and I'll try to explain that. And then we'll take your questions, and we'll actually answer them in parallel with this group. So we'll do a big map task and answer your questions. And also, if you're interested in specific areas of what we've done, we can give you sort of the right person to talk to who can tell you more about that area. We even have 1 or 2 people who could give you a demo if you want afterwards. Okay, so why did we do what we're doing? Well, because for a long time, like I grew up in the database era, sort of embarrassed. People would be like, well, "What do you do?" I'm a baseball player. What do you do? I'm a musician. What do you do? I do databases, right? So it's sort of embarrassing. So at parties you hide in the corner, but now we do big data, and big data is on the front page of the New York Times every so often. And so actually we have been doing what it says there, working on a framework to allow construction of large-scale analytical queries on unstructured data. We have that. We're about to talk about that tonight, and so it's cool stuff, right? And so we're not embarrassed anymore. So what about big data? So basically, as we all know, there's been a ton of stuff. We're all tweeting, hopefully, right now about Asterix DB and other things, and all this sort of digital exhaust is getting generated behind all of us. Status updates and check-ins, and there's all this stuff that companies are starting to realize has lots of value. There's a lot of different places in healthcare and so on where they're realizing if they look at public data, they can see trends ahead of time that the real healthcare people will see a few days later, and so on. And there's also sort of a large quantity of users now generating this data. So Facebook has roughly 1 billion active users. Twitter has lots of users. They're all doing stuff. So the world looks like this. We have people doing stuff. That stuff is happening in sort of different ways. It's all getting amassed, or could be amassed somewhere, and is being amassed at some places, as we sort of read about in the paper, even recently. And the question is, like, where, other than that, could we store this data? How could we find a way to sort of store and make use and get value from this data? And that's a lot about what big data is trying to do. And we'll tell you kind of how we think we can help with that. And so we're sort of aiming at a sort of a web warehousing or big data warehousing kind of use case, and we'll say more about that too. Okay, so let's do history lesson number 1. So there's the database world, and some of you, how many people would say you're like a database person? Okay, so there are a few, but not so many. So the database people would tell you, we've been doing this already. What part of big data didn't you understand, right? So enterprises have been wanting to store and query historical business data forever. In the 1970s, we had megabytes of data to put somewhere, or maybe gigabytes of data we could envision being around the corner. And that sort of big has changed over time. But in the 70s, we had relational databases with SQL. In the 80s, people realized that to deal with large amounts of that stuff, you might want to use multiple computers, and so parallel databases were born. Research at University of Wisconsin generated a system called Gamma. University of Tokyo, a system called Grace, which are kind of the two sort of big initial systems. Teradata, which is located just sort of nearby here, and some of you may be affiliated with that, and others of you may have dealt with it sort of in your workplaces. It's a big parallel database system that was born in the 80s and has been doing sort of shared nothing, parallel, high-performance query processing for years. And there's been a rebirth. And so in the 2000s, you see, like in the 90s, there was a lot of sort of research related to that happening. But in the 2000s, a whole bunch of companies, Netezza, Asterdata, sort of the list there, Data Allegro actually located just about 10 or 15 minutes away from here. All these companies sort of were trying to be sort of the next Teradata. And it became clear that there was a market and a lot of interest in dealing with big data, being able to do that in a more commodity kind of way. And all these companies have been quite successful, at least to the point of being acquired by other larger companies, mostly for at least hundreds of millions of dollars, one of them for over $1 billion. And so this has sort of been a big space that's been exploding. Underneath all of this, ever since the 1980s, is the idea that you can parallelize something by sort of hash partitioning or partitioning your data across multiple computer systems that don't share anything but a network. They have their own processors, their own memory, their own disks. And you partition the data and you parallelize the computation. You send the computation to the partitions. And so this has kind of been the history of big data in the database world for doing parallel query stuff. For doing online kinds of things where you're trying to sell things on the web, sort of manage auctions at eBay, or sort of do sort of online commerce in Amazon or whatever, the OLTP applications are underneath those, generating big data, but also needing to scale. And again, shared nothing is one way that those have scaled. And so as an example, as far back as the 1980s, again, this is ancient history, Tandem had a system called Nonstop SQL that was used widely kind of in financial services and other areas to do transaction processing, again, in a shared nothing architecture. And so that's kind of the world of databases. And they ended up sort of offering us, as potential customers, a stack of software that looks like this. And so at the top, you talk to these systems through a high-level language called SQL, which a bunch of you have, I'm sure, sort of dealt with and at least heard of. So you talk in a language that says, this is what I want the system to do. Find me the employee and department information. If the employee's in the department and the department's on the 10th floor, you can write that as a SQL query and get your result back. And if there's lots of employees, that can be done in parallel on lots of computers. And so at the top, there's the SQL language, and then the software stack has a compiler that takes your request and turns it into the way that the system is going to process it. Has a data flow layer that executes that sort of the query plan that has been decided for your query. And at the bottom, that is executed over a whole bunch of storage managers, running on multiple computers, each doing their piece of the task and kind of feeding the data flow. And so in this architecture, there's one storage manager per machine and a big parallel cluster. Sort of tens or hundreds of computers typically in parallel database kinds of configurations. They tend to be fairly high-end machines. The upper layers are orchestrating sort of the execution of the lower layers. And in fact, a lot of those sort of 2000 era startups took an open source database and some orchestration software and created a parallel database that way using partitioning. And then at the bottom, there's the storage itself, which can be row-oriented or column-oriented, if you've heard about that. But there's these 3 layers. Storage manager per machine, the upper layers are doing orchestration, and then you have the bottom. The thing to note about this stack is it's closed. So a couple things. So one is, if you want it to be parallel, you have to pay for it. So Teradata will sell this to you. Oracle will sell you something. IBM will sell you something. All these companies have products that are based on this, and they're not necessarily cheap. And you can only talk to your data through SQL, right? So you can ask your questions and organize your data. You have to think about how you want to design your data. You sort of design the database, you put your data in the database, and then you talk to it through SQL. And so it's kind of a closed one-way in, one-way out stack. And that's the world of parallel databases. And for those of us in the database world, it's like, what more could you possibly want? You have a great language, it runs in parallel, our job is done. Wrong, apparently. So in the systems world, kind of the distributed systems world, the web started to happen while we were sort of patting ourselves on the back about our parallel databases. And in the late 90s, companies were facing the need to index and query web data. And so there are companies that sort of tried to use database technology early on to do this, like Ink2Me. If any of you remember that company, they were sort of a pre-Google search engine company that was pretty cool. They tried using database technology and concluded they needed something like it but different, and built their own. Everyone needed to do something and realized they had to build something. And so sort of leading into where we are in big data today, the most significant player was probably Google, which had sort of a few thousand Stanford PhD graduates and lots of money, and needed to do something. And so they said, okay, how do we store big data? We need a big file system with big files, right? So that would be a way of having big data. And so they basically made it possible to have byte stream files, sort of the usual file system model that spanned thousands of machines potentially, to make that system replicate data so that if you come up to the system and you ask for your data, there should be a couple of copies of your data somewhere so that somebody will have it sort of at all times that you can talk to, so high availability through replication. And they built that as a service for storing like the web index that they were creating. The next problem you have if you can store big data is you have to write big programs to process it. And so you need to do parallel programming on these machines. And for many, many years, people have been studying how to do parallel programming, and there's lots of cool papers about it. But nobody had really figured out a way of doing it effectively, write message passing programs or try to figure out parallelism from non-parallel programs. What Google said was, we have an idea, we can steal some things from functional programming, and we can offer what we now know as the MapReduce programming model, where you think about one piece of data, right? And what would you do with one piece of data to do your task? You do a map function, which takes a piece of data and produces a key value pair. And then everything that has the same key would get routed to another task that gets to see everything with that key value and reduce it into something else. And then if you need to compute something more complicated, you could do another job that does that same thing. And so they basically said, you, Mr. User, or Ms. User, you need to think about what you would do with one piece of data and one group of data that has common keys. And all you have to do is think about that. Don't think about messages or parallelism or concurrency. Just think about sort of in a data-intensive kind of way, and we'll take care of the rest for you. So they would then apply your functions to arbitrarily large amounts of data. And so basically, you could characterize this as a parallel programming for dummies model. You don't have to understand message passing programming to write a program that runs against terabytes or even petabytes of data. The MapReduce runtime does the heavy lifting. So this is a huge thing for people who need to process large amounts of data and do it in a timely kind of way. So pretty soon everybody wanted this, right? So Yahoo said, hey, we could use that, Facebook could use that. And so the file system work and the MapReduce work, the papers were written by Google and were taken as specifications, and basically open source equivalents were born. So HDFS, the Hadoop distributed file system, which MapR now has an alternative to, the Hadoop MapReduce programming paradigm, those things became specifications from Google to the open source world, and we were given Hadoop and the Yellow Elephant and the distributed file system, and they're in wide use today. That's why you guys are here meeting every couple months. If you go on an annual basis up to Santa Clara, the number of people there for the Hadoop World kind of conference is like doubling every year, and so this is an exploding area. What we've seen happen, us, the community, is that MapReduce is really cool. It enables people to write Java code to process their program or their data with their little sort of data minds as opposed to thinking about parallelism. But it's a tedious way to solve problems. So pretty quickly people want to do something else. And so Yahoo said, okay, we have some ideas from declarative languages and databases. We can invent this thing called PIG, which is essentially kind of a relational algebra-oriented language that processes data in steps, and you can write those steps in a high-level way, and we'll compile those into MapReduce jobs. IBM had a language called Jackal that had a similar concept, and Hive is the other sort of famous, the big gorilla from Facebook, which is essentially SQL for parallel data compiled to Hadoop. And these things are in heavy use. These were some numbers from a while ago. Yahoo said, for their own site, they were seeing over 60% of the MapReduce jobs a couple years ago being pig jobs. Facebook was saying, over 90% of their Hadoop jobs were actually Hive queries that had been compiled into Hadoop jobs. These numbers are probably higher today. We've been talking to a lot of different companies. We've made a visit to Netflix, and we have Pig and Hive, and pretty much all of our MapReduce jobs are one of those two. Pig are for the ETL kinds of or data transformation jobs. Hive are for more the query kinds of jobs. But this is pretty much now how people are using MapReduce. They write Pig programs or they write Hive queries. And there's a similar sort of story at Microsoft where they have a file system called Cosmos, runtime called Dryad, and some high-level languages called Dryad, Link, and Scope. Scope is what sits underneath Bing and kind of powers their back end. And so this has kind of been the trend in the distributed systems world in parallel with what happened, but slightly later than in the database world. And then similarly, the big data world has sort of their equivalent of OLTP. If you want to build gaming sites or you want to deal with user profiles when users log in really quickly, you need something which is sort of quick and dynamic. And so the so-called NoSQL systems were born, or the key value stores, so where you can sort of store something by a key or get it back by a key. Here's a user ID, get me the user profile quickly, and do very simple things with records, not have to talk through SQL. And so these things are characterized as being fast, highly scalable, and highly available for storing vast amounts of data if what you want to do is get and put, essentially, based on a key value. And again, sort of Google invented one called Bigtable. Amazon invented a proprietary one called Dynamo, which they were using kind of inside their systems. And then sort of open source versions of those came out of the papers that were published. The Bigtable spec gave us HBase, which runs in the Hadoop world. The Dynamo spec gave us Cassandra, and so on. And so again, in the open source world, there's a software stack. And so this is kind of an artist's conception of the open source, the stack that sort of this meetup group is about, which is the open source Hadoop stack. And so at the bottom is HDFS, the Hadoop distributed file system, where the idea is the world's largest files can be stored here. Right? So there's giant byte sequence files at the bottom. If you're writing an analytical program, kind of using the MapReduce paradigm, you're writing your map functions and reduce functions and creating jobs and executing. That runs on the blue layer, the Hadoop MapReduce layer. And basically that takes and runs your map job against all the data, then reshuffles the data sort of based on keys and sorts the data based on keys, feeds that into your reduce tasks, and those things get to process the groups that they've been promised to see. And then you may have a job that does a sequence of those. And so that's happening at the blue layer if you're kind of rolling up your sleeves or already wearing short sleeves like I am, and you want to write kind of MapReduce jobs. If you want to do key value stuff, HBase sits on top of the Hadoop distributed file system and gives you sort of record level get and put. And then at the high end, if you're more interested in writing sort of quickly and getting your results quickly in terms of working at a very productive high level, you're writing Hive queries and talking HiveQL, or you're dealing with the Pig system from Yahoo and Hortonworks and doing Pig Latin, or maybe using the Jackal facility and IBM's sort of big data story. And so you may be talking at a high level. What's different about this picture is a couple things. So first of all, it's not a closed thing where you can only talk to it through HiveQL. It's open. So you can use multiple languages to talk to the same data. You can run a MapReduce job in the middle if you need to do that because you're doing something complicated. You can even just talk sort of key value get and put operations, or you can do high-level language. And so it's sort of an open stack. And if you don't like what's there, it's open source and you can get it and you can muck around with it and improve it sort of in your own company. And so we've seen, like you see for Linux, you see sort of different lines of Hadoop and different versions and so on. And so this is sort of the open source version. And so now the database world is sort of paying attention, looking at this going, this is pretty cool. Everybody loves big data. They're talking about it at parties. Look at this architecture. What do we make of this? And that's kind of the database answer. It's like, wait a second. Who said that's the right way of building a system? We actually figured out how to build these systems. The fact that we have this big byte sequences is not necessarily the best underpinnings for a high-level language. We don't necessarily want to have to sort of compile SQL down to map and reduce. Why do we have this architecture? The answer is because this is how it grew up. It's sort of an accidental architecture. It's very effective because it's there. People have big clusters. But if you were to sort of know from the outset that you were going to do Pig or you're going to do Hive, you might have a different architecture. And so that sort of got us thinking about, like, what should the next generation architecture for big data management look like? One other thing about existing solutions, and sort of this is at the current point in time, and then I'll tell you more about Asterix DB. And so if you're sort of a web company and you're trying to do something, you start out small and you put your data in MySQL because you like the price, it's free. And then you realize, maybe you're not getting the performance on your website, and so you put some memcache in front of that. And then your business guys start asking questions about what's going on. And so maybe you have to roll in Hadoop. And maybe at some point you decide you'll try one of these NoSQL things. And then pretty soon your programmers are saying, I just want to ask a query. Why do I have to write MapReduce? And so in comes some combination of pig and hive, probably both. And then you have to figure out kind of how you move data among all of these things. Right, so there's the bubblegum and baling wire that kind of puts all this stuff together. That seems to be what a lot of the big shops look like today. And so this was kind of our take on what was happening. I actually gave this, or a version of this talk, about a year or two ago, sort of behind someone else who consults in this area. He had a very similar slide, except he was from Europe and he had duct tape and chicken wire. So after the talk he came up and said, the real problem is there's no standards. Is it baling wire or chicken wire, and is it bubblegum or duct tape? If we could solve that, we'd be done. But seriously, this is what people are sort of doing and seeing. We also had a visit from people in our med school about 2 weeks ago who are doing some work with Hadoop. And basically they're gluing together sort of MongoDB and Hadoop, and they're using multiple languages. And he went, it's pretty interesting that you chose sort of these pictures because this is what we're doing. And so anyway, that's something that you see right now. And the question is, do we need that many systems and have to solve that many data integration problems and data migration and data movement problems? And so we said, okay, let's think about, because we're at a university, we get to stop and think, and we don't have to ship a product, except tonight we're trying to, kind of. Let's think about what would happen if we were to build the next generation system. And so what we did was to say, there's sort of like 3 areas that we should be drawing technology from, ideas from, and trying to figure out how to create a best of thing by putting them together. And so at the bottom left is parallel databases. So again, we just went through the history. There's a lot of knowledge there about how to process big data very efficiently. What are the right algorithms for doing parallel stuff? How do you avoid having to sort data all the time? What are the greatest hash-based methods for doing things fast? A lot of good ideas from there that can be brought to bear on the world that Hadoop has. On the right-hand side, the Hadoop world, sort of the data-intensive computing, or big data as it's called today, world, has a lot of sort of value also, and I'll talk about that on the next slide, where the parallel database sort of community missed the boat on some things that would be good features for their systems. And then finally, data is not so structured necessarily anymore. And so a lot of companies have Teradata for their traditional relational stuff, for their business data, but then they're using something else or some combination of something else's for dealing with sort of the digital exhaust that they want to analyze and get value from. And so there's semi-structured data management. There's actually been work done in academia on that since about 2000. And so there's ideas to be drawn on there about how to think about semi-structured data. And we said, okay, let's actually think about, if we had a big cluster, taking ideas from all 3 of them and creating a system that sort of is a best of or a learns from kind of system. And that's what Asterix DB is about. So the triangle is kind of our drawing from these 3 different areas. And so the project, what have we been doing? So basically trying to build this new, what we're now calling a BDMS, because the term big data was coined a couple years ago while we were in flight. The idea is to run it on the same kinds of clusters that you see for Hadoop, on Hadoop-style clusters, to handle really massive quantities of semi-structured data, and I'll tell you what we mean by that. To have it be openly layered, because people seem to like the idea of being able to choose. Do I always have to use that language, or can I come in and write a program against that data with some other technology that I like? And so we want this to be openly layered and to interoperate with other kinds of data. We'll talk about that. And then the goal was to share it with the community, and that's what's happening right now. We've also been doing research and have a research agenda going forward, and this is going to become our laboratory for doing it, on sort of big query processing and dealing with big workloads on big data, doing highly scalable sort of storage and index management, applying ideas from HDFS world back into the database storage world, also dealing with sort of fuzzy data. So one of my faculty colleagues, Chen Li, who's here in the back, Chen, if you want to raise your hand so that you can especially ask him hard questions about this area. He's like a world expert in fuzzy matching, so you can ask him any question and he'll give you a fuzzy answer. And so, but he'll, the answer's in there. And he'll actually give it to you in small pieces called grams, and then if you reassemble them, it's the answer to your question. And so we also, in this world, data is dirty, queries are dirty, you're sort of speaking into your cell phone or typing in your cell phone, working sort of quickly on the web. Things rarely match perfectly. And so we also wanted to have sort of special technology in our system for dealing with that, and we'll talk about that. Everything is happening with locations when people enable that on their cell phones. So spatial data, simple spatial is really important. And everything has got times and dates associated with it. That's important. And so we said, as we build this thing, it should be sort of friendly for fuzzy questions and also deal with spatial questions and temporal questions. And do all this in the context of one shared nothing scalable parallel system. And so that was our goal. And then we're also doing some sort of novel stuff about what people are sometimes calling fast data or high velocity data that I'll talk about. And then obviously our real goal is, we're a university and our product is, they come labeled with BS, MS, or PhD. And so our product is graduates who want to train people sort of in big data technologies and how to build systems of this scale. And so that's another of our main objectives. So you can see that we have sort of t-shirts that are sort of big data graduate in training for most of the people wearing those. Okay, so I'm going to tell you about Asterix. Right before I do that, here's some of the things that we're trying to not lose as lessons from the world of Hadoop as we create something different. So one is, people like the price point. Open source is a great thing. The price is right, and so Asterix DB is being offered out with open source, no license restrictions, Apache-style license, because that's what the community seems to want. Non-monolithic layers, talked about that, so you can use the piece that you want rather than using the entire system if you don't need the entire system. We'll talk more about that. Equal opportunity access to data that has been stored in our system and data that's stored in someplace else, like HDFS, is important. And I'll tell you about how we address that. And then kind of on our roadmap, we've got low-level sort of technology in our underlying platform, sort of not yet rolled out to the higher levels of Asterix DB. Obviously, sort of the roll-forward recovery for long-running things in Hadoop is very important. It gets the job done eventually. In databases, we're more traditionally saying, kind of doesn't matter what happens, either as long as nothing happens or it all happens. I'll come to you and I'll say, life is good, I didn't hurt your data, I had to roll back your job or I rolled your job forward. Roll forward recovery is very important for large jobs when things fail during job execution and you need to get it done. So we're going to be learning from that and again have infrastructure kind of for that. And then it's also sort of one of the nice features of HDFS is you put data in and it finds a place to live. And those kinds of features need to exist also in more database-y kinds of storage. And so we're sort of have a roadmap kind of on that that's part of our current research agenda. So those are sort of the things that we took as sort of really good things that are in the Hadoop world that we need to not lose if we believe we're going to create something different. So this is a one-slide summary of Asterix DB, and then I'll tell you what it looks like for a user. This is kind of our architecture slide. So it's a shared nothing system. Each one of those boxes is a separate computer with some disks and some memory and some cores attached to it. It runs basically sort of an Asterix system instance. Those things are coupled together, and you can execute parallel queries much as a parallel database does. So at the bottom of this, there's a storage layer. The bottom two boxes are essentially Asterix storage, and I'll talk more about what they look like from a user perspective in just a minute. But essentially, we have technology based on what are called LSM trees, log-structured merge trees. Think sort of what's inside HBase for storing data in a B-tree kind of way and other kinds of ways that I'll talk about. So there's like a storage layer that stores components of your data, and then those things are integrated into a logical concept that I'll talk about called the data set or a data feed data set. So at sort of the bottom two layers are data storage. Just like in the other pictures, there's a layer in the middle that does query execution. We have an execution engine called Hyrax that I'll talk a little bit about. And then on top of that, we take in queries in a language and compile them into Hyrax jobs. And we consult a metadata manager to understand things about our data. And I'll give you a clear picture, hopefully, of that stuff, too. And so to a first approximation, that looks like a traditional kind of database architecture. But it's got a very different kind of data model, query language, and openness to it. As compared to, for example, a relational system. And it also is a parallel sort of shared nothing open source thing, which is also something that you don't get in the world of databases today. You can get open source databases, but they're not sort of large scale parallel. And again, we'll have more, we can sort of answer questions more about that at the end. The basis for this are a data model called the Asterix data model, and I'll explain more about that, and a query language, which is fully NoSQL compliant, right? So NoSQL is all the rage, but we have NoSQL here. We have a language. It's a query language. It's called AQL. It's not SQL, so we can check the marketing box saying we're a NoSQL system because we have NoSQL. We have data coming in through loading the data or feeding the data from external sources or from inserts or deletes happening through the AQL query interface. You can ask questions through the AQL interface. They can be little questions looking up sort of points of data, medium-sized questions looking up ranges of data, or large questions doing large correlations across multiple data sets. All those things are within kind of our target for the system. And then we kind of have the dotted box in the future. We would also like to support like continuous queries and data publishing from the system. That's another research agenda that we have. And I'll talk a little bit about that at the end. Okay, so user experience time. So what if you were to, as all of you are surely to do, download the system sometime tonight, because you can't wait till tomorrow, because you might get one of these, right? So you get the Asterix data model as the way of thinking about your data if you get our system. And so what is the Asterix data model? It's basically kind of the world of data as you see it when it's in our world. In the world of databases, you create a database. This is, sort of 2013. Databases have been around since the 70s, and so no more databases for us. You have a dataverse, your data universe. And so you create a dataverse. It's a place to put all the data that's sort of related to something you're trying to do. And so we have a demo that ships with the system. This is sort of descended from that. So you might create a dataverse called Little Twitter Demo, easily written and said. And you would create that dataverse. It's now a place where you can create a whole bunch of things that you want to store that might be about this demo that you're trying to create. You can create data types. And so if you know some things about the data that you're going to be dealing with, you can tell the system about them by creating data types. And then you can create data sets to store that kind of data. And so this is a fairly complicated looking example, and I'll simplify it in a minute. That is what you might store if you're sort of camping on one of the Twitter APIs and getting the stuff that's being fed to you in JSON form. It feeds you things that look like this. And so a tweet message, what this says, it's kind of like a Java class or pick your favorite language, a little bit like a database schema, but it's a richer kind of language. You could create a type called tweet message type for this data as open. I'll talk about that in a second. With a tweet ID, which might be the, the unique identifier of the tweet, which tweets have, might have embedded in it a little nested record that has information about the user. So in this case, their screen name and the language that they're tweeting in and how many friends they have and so on. That snapshot of that information gets sent with the tweet. And then you might have some other information about the tweet, like where did it happen, the sender location. That's marked as a point, so that's sort of a two-dimensional piece of spatial data. It's marked as question mark because it's optional. That's our way of saying nullable. So a tweet might or might not have that. Not all tweets. In fact, the majority of tweets aren't yet location sort of tied, but more and more hopefully they will be, so the businesses can sort of do what they want with that information, and so can healthcare organizations and so on. Tweets are tweeted at a particular time, so that information is there. A tweet might be about a set of topics, and so might have a hashtag like Asterix DB, hint hint, and so that tweet, one of the referred topics might be Asterix DB. And so that you might have that set of topics, a bag of strings essentially, attached to this piece of information that you're going to store. And then probably you should keep the whole thing, because if you didn't extract what you want, you can go back and look at it tomorrow. And so the whole message, the whole tweet message might be stored as well. So for whatever application you're building around tweets, this might be what you've decided you'd like to do. And now you need to create a place for them to live. So that just says what they look like. Then you have to create a place for them to live. And so you'll create a data set. That's sort of the table-like concept that we have. You have data sets that are typed. And so the type is tweet message type, and the data set is called tweet messages. And all we require you to say, kind of in addition, is you need to tell us, like, what's the unique thing about a tweet that I can use to find that tweet if you ask me. So to sort of think key value store in a way, you have to identify like the main key, the primary key for the tweet. And we use that under the covers to partition tweets across a large cluster. So we do some hash partitioning today on tweet ID. And so this would create that type, and that would create the set of messages. So a little bit more about this. So first of all, our model, so where it came from is looking at JSON, which is very popular these days, and saying, what if we made JSON a data model? Thinking as database people, what's it missing? Well, it needs to have a richer set of types. We need spatial and temporal and so on, in addition to the basics that it has, because now it's a data model. It's not just a transition format from one machine to another. We also would like to be able to have sort of rich constructors to build up interesting types. And so this example has a nested record and a bag of strings. So we have records, lists, and bags, and you can compose them arbitrarily to create interesting objects. We have an important idea, we think it's sort of an important idea, of having open types. And that's the default if you don't say. If I just said create type tweet messages, it would be open. I can say as open or as closed. If I say as open, what I'm saying is that's what all tweets will have. They'll have a tweet ID and that user info. They might have a location. If they do, it'll be a point. So I'm telling you what a tweet will have. It could have a lot of other stuff too. And so it could have additional attributes. That's okay if it's an open type. And so the type spec is kind of like, it'll have at least this stuff, but it could have more. If you would like to have something more like a relational model where your data is what you say it is and nothing more, then you could say as closed, and then we wouldn't allow additional attributes to be on your data. But if you say as open, everything that's a tweet message will have that stuff, but it could have anything else too. And then finally, we have a notion called external data sets, where instead of actually saying what you say here, in which case we will create storage and manage storage for your data, you could actually make what's called an external data set specification, and you can see examples on our website that I'll point you at later. And you can point at data that's in HDFS, already being sort of accessed by Hive, and we can access it too. Or point at data that's stored in your local file system that maybe is in a delimited file, and we can access that as well. So you can create a data set that accesses external data, not just stored data. And then we have a notion called data feeds that I won't elaborate on right now because I'll get to it in a couple slides. So that's our data model. So we've invented sort of this basically, so we think it's a common sense sort of extension of JSON to be what it would be if you wanted a data model for that kind of data. So semi-structured because if you wanted to, you could just say this. You could say, I want to create a type called tweet messages with a tweet ID, and there's going to be other stuff, but I'm not going to tell you ahead of time. That would be fine too. You could just say that much and start your project and build your app, and your app would run just the same as if you'd done the other thing. The thing is, when you went back to think about what was in your data set, you wouldn't really know because it could be anything. But you can choose. So if you like a world where you don't want to prescribe ahead of time what's going to be in your data sets, we support that world. But if you know what you want, you can also tell us up front, I should say, that you're going to do that. And if you do tell us this information, we'll exploit that. We'll separate out the schema information from the data, store it somewhere else, and not every piece of data will carry all that information. But if you tell us instead this, you can still store the same data, but each piece of data will have to know what's in it. The data items will be bigger because they'll be carrying your schemas as well as their data. Your choice. We'll support both. And so that's kind of the openness that we think is important. Again, the idea is the semantics of your app and all your queries and everything else will be the same regardless of whether you say the first thing or the second thing. If not, you can file an issue on our website, which we'll point you at later, because that's how it's supposed to work. Okay, so this is just an example of some tweets. We won't go into the details there. We have a query language, AQL, the Asterix query language, and this is like a first example of a query. So suppose you wanted to know, like from that data set that we created a slide or two ago, what is the user information and what did they say for all the tweets that are related to, actually this slide is slightly out of sync, that are from the user whose screen name is D. Flynn. Okay? And so what you do is you declare a variable called tweet. You say for tweets that are in the data set of tweet messages. So that specifies that you want tweets from that data set. It binds that variable, think about it sort of one at a time to those tweets, checks to see if the tweet's user record's screen name is dflynn24. And if so, it'll create a new instance of our data model, which has two attributes. The first one is called tweeter, and that'll be that user's record. And the second one is called tweet, and that'll be the message text. And so you've got a bunch of sort of stored data. You want to create some summary or some other kind of data from it. You can express that in our query language. And so it has a whole bunch of features, and you can learn about that by sort of looking at our beta. It has a special support for similarity matching. I'll talk about that in a second. It supports spatial predicates, so we could have said something about the location of the tweets if you wanted. You can do aggregation. I'll show you that on the next slide. And there's more sort of in the works in terms of features we expect to have. But it's a pretty rich query language. It was inspired by sort of looking at what's in the language X query, which deals with the semi-structured data of XML, and throwing away a whole bunch of stuff that's XML specific or kind of crufty, keeping the core ideas from that language and then sort of making that a new language for querying this sort of JSON extension kind of data that we have. So that's sort of a quick introduction to AQL. If you wanted to do something more complicated and say, okay, so people are tweeting about stuff, tweeting about Asterix DB today. They're tweeting about Verizon because of the news, and so sort of, if I wanted to go through and find what are things people are tweeting about in those Verizon-related tweets, what are the other topics, and I want to know like how many things are about that topic are being tweeted, you could express that as well. I won't take you through the details, but it requires a variable that looks at the tweets, a variable that looks at the topics inside the tweets, kind of flips them inside out and says, okay, group by the topic, and then tell me like what's the topic and what's the count. Details sort of unimportant for getting you the idea of the kinds of things you could do, but then you would get back, okay, for the Verizon topic, there's 3 tweets. for topic commercials, there's one tweet, and this is sort of how many from the slide 2 slides ago would have satisfied them. So that gives you a rough idea of the kinds of things you can do. So you can sort of slice and dice your data and aggregate and so on, restructure, and get something new of a different shape with different information out of that across multiple data sets potentially. Okay, special support for the case where things don't quite line up. And so if you wanted to look at tweet messages and sort of ensure that the tweets are not the same tweet, so there are 2 messages in the tweet data set, same data set with different IDs, but the text is kind of the same. And so the red operator is our kind of equals operator. That sort of says, I want sort of rough equality rather than actual equality. I want a fuzzy match between those 2 messages. There's a way of sort of controlling what that fuzzy match means, but for string data, it means edit distance with some default parameters that you can also control in the context of this query. What this will do is find pairs of tweets that are similar, message text-wise, similar in terms of their content, and show you that pair so you can look for things that are similar. You'd probably want to restrict this a little bit because you can get a lot of data back, potentially, if there's messages that meet that similarity criteria. Okay, and then finally, sort of future work that we have, there's a secret feature inside our system which we haven't documented yet called data feeds, but it's running in the lab, where if you would like to have data continuously coming into your system, you can create, instead of a normal data set, you can create a feed data set. It's just like a normal data set in most ways, except that it's sort of attached through an adapter to some outside source of data. And so the first example there is creating a data set that is sort of attached to the Twitter stream using a Twitter adapter with a sampling interval of 10 seconds. There's, for feed data sets, the opportunity to specify a function that gets handed the tweet on its way in, that can process the tweet and add information to it before it's being stored. And so you might have a function that's adding hashtags to tweets, looking for those hashtags and putting them into that sort of referred topics attribute. And then the rest of the properties are the same. So you say what's the key, and it'll be partitioned by that. Likewise, you could build something for other kinds of sources, for example, CNN newsfeed. You can also, just like regular data sets, you can index these data sets, and so you could create a location index on sender location of tweets. We support B trees, R trees, which are a spatial index. We also support sort of inverted text indexes. And so you can sort of use a rich set of different kinds of indexes to index your data so that queries can be then efficiently processed so that if they have location predicate or a text predicate involved in them. And then once you've created these 2 feed data sets, you start the feed and data flows in. So this is different than data streams because data is not like flowing in and you have to catch it while it's there. This is a keep everything kind of feature. So this is basically kind of attaching a hose to a data set, and the data set's getting fuller and fuller while the hose is attached to it. And so it's a keep everything thing that's about data ingestion, so you don't have to write a program that's kind of orchestrating the Twitter stream and doing inserts. You just hook a data set into Asterix, plug it in, and data will come in. And all the queries that you would have done over that data set of tweet messages from before, you could still do over this data set because it's just the data set. Okay, so that's kind of the end of our user model. I just want to spend kind of the last few minutes of the talk giving you a quick overview of what's under the hood and why it's more like the Hadoop world and less like the database world, but also how it's different than Hadoop. And so again, we have sort of multiple layers, multiple components, and an openness that you don't find in the parallel database world. And so at the bottom, we have a data parallel platform called Hyrax that I'll tell you a little bit more about. That's our parallel runtime. That's our alternative to Hadoop. So we're not actually based on the Hadoop stack. We are sort of a peer, if you will, of Hadoop. And sort of the interoperation thoughts in terms of working with Yarn and so on. But it's a different execution platform, and I'll say a little bit more about that. At the next layer up, there's sort of a middle tier where there's a layer called AlgeBrICS, which is about sort of doing algebraic operations over big sets of big data. I'll say more about that as well. We also have a MapReduce compatibility layer that we've got running in the lab that we will open source down the road, hopefully fairly soon, where you can run your Hadoop jobs kind of out of the box on our system. And it's sort of emulating Hadoop, but sort of more quickly than Hadoop in this world. And then we have some other byproducts that we've done that we can tell you about kind of after the talk if you're interested. A lot of people these days are interested in dealing with big social graphs and doing big graph analytics. And so Google published a paper called Pragel, and being open source people, we said, okay, that looks like a software specification to us. And so one of our students who's here tonight who can talk to you afterwards basically built a clone of Pragel using our Hyrax technology, and it has very good performance and scalability. So if you're doing big graph processing, ask us about Pragelix, part of the Asterix family of software, I guess. And then if you're doing big machine learning, we're doing some joint work with UC Santa Cruz around big data support for machine learning. There's a thing called iterative map reduce update that we're doing with them that also runs on the Hyrax platform. So there's a bunch of work sort of using that same platform that we've developed. That's the oldest part of our system. Work on that sort of started in early 2009. So that piece is relatively mature compared to pieces that came in later, which are have been under development for fewer years. And then at the top, again, we have multiple components. The green thing is Asterix, our system. That's what we're giving you sort of tonight, sort of making open is the Asterix DB system, which has the Asterix query language at the top. And so if you talk to us through the green thing, that's kind of your database stack. But you can use other components. And people have built other things. And so the same student who was working on sort of graph analytics also, we did sort of a demo for Facebook where we took the Facebook Hive system and sort of pulled the bottom out from it and plugged our system underneath that. We could tell you more about that, creating the thing we call Hysterix, which is essentially Hive running on Hyrax. We've done that sort of using this algebraic layer. And then people have sort of talked about how you would build other high-level language compilers. There's an Apache project doing something called BXQuery, which is the big parallel XQuery implementation, also using the red layer Algebrix and the blue layer Hyrax. And so I'll sort of tell you a little bit more about each of those pieces before we wrap up. So let's sort of go top down. So the top, the green thing I told you about, that's Asterix DB, and we'll tell you how to find out more about that. The next layer down is for those of you in the audience, and there might or might not be any of you, who are thinking, I've got a great idea for the next big data language, and it's not this nonsense I'm listening to right now. It's also not SQL, it's something else, and it's going to be great for processing this other kind of data. If you're trying to build a big data language, there's a bunch of stuff you have to do that we've had to do several times, and that others are having to do. Everybody who builds a big data language has to do a lot of stuff in common. So they have to have some sort of a data model. They have to have physical operations to process data. They have to have an optimization framework if it's a high-level language. And so what we've done kind of with the red layer called Algebrix is to factor that out into a reusable component where a bunch of that stuff comes with Algebrix. And then you can add things that are specific to your language. And so instead of writing, sort of 50,000 lines of code, I'm making up a number, you can borrow 40,000 and write the other 10, essentially. So you can write sort of, a piece of something that you would have had to write all of. And so that's been the goal of Algebrix. And we drove that out of sort of creating this Hysterix thing from Asterix, factoring out the sort of data model independent stuff. And so this is just a piece of technology I'll tell you about. It's under the hood, but if this sort of resonates with something you're trying to do, we can talk to you more about that. Ultimately, Algebrix stuff turns into things that are executed on the Hyrax platform. Hyrax itself, it's actually, so the upper right corner, those are Hyraxes. It's actually, so there's a website that we have for Hyrax. There's a video link there, you can go learn about them. They are the closest living relative to the elephant, so chosen for obvious reasons. Except they cluster well, right, and they're really cute, so how can you not want that, right? You can't leave today without having one of those things, right? They would make a great pet. An elephant, have to clean the backyard would not be so great, but those things, they're smaller, right? So, fewer droppings and things. And so that's a Hyrax, and so actually that's what our Hyraxes look like. That's part of our logo. It's a partitioned parallel platform for data-intensive computing. So what does that mean? Basically, we're using the same kinds of ideas that are inside parallel databases and also inside Hadoop to deal with large amounts of data. A Hyrax job is a DAG. It's not just MapReduce job over. It is a whole sequence of operators. And it's not just a string of linear operators, map or reduce. It's actually can be sort of a filter operation followed by, with another filter operation in parallel, feeding a join operation, feeding an aggregate, things like that. More complicated things that look like sort of the query plans that parallel databases use to do things more efficiently. And so operators, the boxes, they consume and produce partitions of data, and then connectors, the lines, route data, repartition data based on things like hashing or just hand it to the next guy or range partition or other kinds of repartitioning or replicate this information. There are various kinds of connectors that can be used to connect the operators. And so a Hyrax job is sort of a rich sort of data flow program, essentially, that is then executed in parallel on your cluster. How does Hyrax compare to things you might have heard of? So sort of it's based on using parallel database ideas and applying them to sort of the big data world. And so it's using well-known ideas, but packaging them in a way that's sort of very componentized and reusable, as opposed to being just inside some system in a layer that you're not allowed to touch. versus Hadoop. It's a more flexible model. It's a DAG model with rich operations that have multiple inputs, as opposed to just map and reduce. And it's also a much less pessimistic, I think you could say, implementation. What Hadoop does is, in order to run very large jobs for very long periods of time, under sort of conditions where disks might fail because your job is taking 8 hours and 6 hours in something goes away, it sort of tries to persist everything. Every time you do a map reduce job, writes the result to HDFS. Sort of in between map and reduce, it always sort of has files going on. So rather than sort of pipelining things, always sorts the data. So it's a rigid model that works really well, but it's a rigid model and not necessarily the most performant way to run a query. And so our system supports a model like that, but also supports much more sort of rapid pipeline models as well that can be used to get much better performance on queries. So it's not difficult to sort of run much faster than Hadoop if you don't use sort of the same pessimistic implementation. MapR guys will tell you the same thing. And then what about Dryad, which is from Microsoft, which was for a while a contender. Microsoft is actually now doing Hadoop as well. But basically Dryad, sort of a circles and arrows model, but they didn't have a notion of data and data flows and sort of out-of-the-box operators. So this is sort of like a level above Dryad. So this is where sort of Hyrax sits in the ecosystem of big data runtimes. Okay, so wrap up. So why would you maybe want Asterix DB? Well, because we think we're like a one-size-fits-a-bunch solution. So we think we can give you better functionality and manageability and performance by giving you one system that you can use to solve a bunch of problems that you would have had to get maybe Hadoop and Hive and MongoDB, as in the UC Irvine med school example, to solve in the past. And so what do we have inside that maybe would give you hope that we could do that quickly and effectively? We have sort of indexing technology and storage technology based on log structuring techniques that can ingest data quickly and then can still sort of run queries over that data. We have support for spatial data, including R-tree spatial indexes, support for fuzzy data and indexing fuzzy data to do sort of quick lookups, support for external data sets and also data feeds coming sort of in a future release. And again, we're sort of working on that quite actively right now for getting external data. And then there's also this sort of graph processing thing that we can tell you about offline if you want, called Craiglix. And then underneath that, we have this Hyrax engine, which has been sort of scale tested out to a large number of cluster nodes, at least from our perspective. I'll tell you more about that in a second, at Yahoo. And it's a very powerful, very flexible system. And again, we'd be happy to tell you more about that and sort of point you at papers and show you how to get the system. It has construction inside based on sort of best-of-breed parallel database ideas. It's not just sort of a simpler engine. And in some of our tests for disk-resident data, running on data that places systems like Hive have stored, if we can run our queries on the same data, we get large performance gains. Sort of a modest sort of middle gain might be 10x. So if you're doing certain queries where we can use indexes and they don't have them, we could sort of beat them arbitrarily. But on things that they're good at, we can sort of do 4 to 10x their performance. So we can, again, tell you sort of more about those results if you're interested. So that's our motto. So more engine, less trunk. Also sort of chosen for reasons that, if you don't get it, that's fine. But think about it. And so Asterix DB is sort of coming out. Where can you learn more? We're like the new kid on the block. And so let's actually, whoops. Click on the link. You can go here. And this is our website. So if you come here, you can get an overview. We have all of our sort of documentation online. Tells you kind of what our system is and more about it. And so there's information about how to get it and install it. There's a sort of a 101 that will take you through a whole bunch of the features. There's a reference guide to the data model, to the query language, to the functions, and so on, that the tired-looking team in the shirts have been working on. And so, we would invite you to come to this site and sort of check it out, download it, play with it. It's intended to run on clusters, but it will run on your laptop as well. And so get it and try to run it on your laptop. And remember, sort of actually getting into the user group and getting the system. And it's a way to get like one of these, right? You want one of these. And so anyway, we'll come back to that. So that's the website. So you're welcome to go there. So where are we? So basically, we started the project in early 2009. We had a little bit of seed money from eBay, and we had money from the state of California. We got a big NSF project that we did jointly with UC San Diego and UC Riverside and UC Irvine that has been running with UC San Diego, doing research on sort of text kinds of things, UC Irvine focusing on the core system, UC Riverside focusing on aggregation, and also some interesting semi-structured kinds of things. All this stuff has come together into a sort of large, and what we believe is sort of an industrial quality code base. As a result of the project. So it's actually, at this point, sort of a fairly large, significant piece of code. It's been tested. It's what we would consider to be scale. What Yahoo would say that's it's a spare cluster in Yahoo Labs, but the cluster has 1,400 cores and 700 disks, and we've run queries at that scale. We actually did a rewrite of parts of our Hyrax system to run successfully at that scale, and so it's sort of ready to go up to that point. We haven't gone beyond that point as of yet, but we believe we have something that scales. Hyrax and Pregolix have been around for a while. Hyrax is something that sort of a few experts elsewhere have been playing with. Pregolix is the graph thing that we'll tell you more about offline if you want to know about it, which is available and sort of intended for end users who have graph problems to download. And Asterix is here. So it has a NoSQL style data model with a not SQL query language. It supports declarative queries, runs them in parallel. You can insert data and delete data, and all that stuff is affecting stored data in the LSM world, or also you can FS deal with your external data through our external notion of data sets. Has some cool features for fuzzy, spatial, and temporal query processing. And we also have I guess we'd say key value style transaction support, sort of NoSQL-like support for doing inserts and deletes and knowing that your data has gotten there or not. We can tell you more about that as well if you want. So this has been a huge effort of a lot of people, only some of whom are here, but all of whom deserve credit. And so faculty here, myself and Chen Li, and research scientists here, Vinayak Worker, who's in the room, who's sort of the Hyrax guy, and Nick Knows, who was here for 2 years from UC San Diego and has now gone off to Google. UC Riverside, we have a collaborator who can't be here tonight because he's giving his last lecture. This is the end of the quarter in the UC system, Vasilis Tsotris. And from Oracle Labs, who's also here, recently joined the project, Till Westman. So Oracle is collaborating with us around this by letting Till work with us and work on this. A whole bunch of PhD students listed here. I won't sort of read all of their names, but a couple of alums have gone on to HP Labs and to Cloudera. What the Cloudera alum was part of creating a thing called Impala, which until today was interesting, right? But now we have Asterix DB. So sorry, Alex, if you're watching this later. And then we have a bunch of students who are here who we can introduce you to if you want, both from here and from UC Riverside. There's also an alum who did some work related to the project, who's at Google, who did some basically interesting text query kinds of things, Nathan Bales. Then master students, we've got a bunch of master students who've gone through and done projects. Actually, we have 3 things coming out today. One of them is the software, and 2 of them are our master students who just filed their theses successfully today based on work that they're doing in this project. We also have a couple of bachelor's alums. And then we have some work with sort of foreign affiliates, mostly in Germany at the moment, but also a bit in India, students elsewhere who are working on projects related to this. We've been collaborating a bunch with industry, trying to make sure that what we're doing is sort of not crazy academic stuff, but crazy industrial stuff. And so we've sort of worked with Facebook, talking to them about what are their problems, what's their architecture, what do they care about, what do they think about what we're doing, and so on. One of our staff, faculty-ish, graduate student-ish people, Vinayak, who's our chief scientist, basically got one of the early Facebook fellowships. They also told us a lot, gave him access to a lot of information about what the workloads look like on their clusters that have helped to inform us in terms of what we think about. Yahoo, we've collaborated with and gotten access to that cluster. They've also given money to some of our graduate students. We've done collaborations with a couple of other universities. And then also there's an Apache project building parallel X query on our system. So we've sort of been talking a lot sort of with people outside. It's intended to be open source. For more information, if you want to know more, again, so you can go to our project page, which is up as of right before this. You can look at our code base at Google Code, either for Asterix or for Hyrax, or for Pregolix. You can go to that page, and it will sort of take you into the world of Hyrax and its sort of other ecosystem. So that information is there. We'd encourage you to take a look at that. We've gotten funding from a bunch of places, and so National Science Foundation has been kind of our biggest funder. eBay got us started. Facebook has helped. Yahoo has helped with machine access and grants to students. We have industrial funding from Google, from HTC, from Microsoft, and a collaborator sort of donated by Oracle Labs. And so we've been working a lot with industry, and we appreciate the support we've gotten. And for those companies who are not on this list, don't you wish you were, right? Because you could get one of these shirts, right? So anyway, sort of thanks to all of those. Also, we have some early adopters, and so this is actually my granddaughter this morning wearing the Asterix DB shirt, which you can purchase if you want for your granddaughters or maybe your daughters, or maybe later for the grad students who don't have daughters yet, at Zazzle.com, right? So that's an option, right? And notice that is fashion, right? If it's not, don't tell me because it's my granddaughter. I don't want to know. But anyway, so that's a current shot of our earliest adopter, like looking for a Hyrax, which is probably loose on the lawn. Okay, so that's it. That's our story. We've sort of taken enough of your time. We're sort of here. I guess we have the room until 8. We have a team so that no matter how many questions you have, we can parallelize and answer all of your questions. We can take them as a big map job, and then we can kind of reduce them and provide more information on our website if there are questions. And so at this point, I'll stop and take questions. Again, one last reminder. So one of the ways of getting a shirt is you can ask the best question that the people who have shirts already think was the best question. So questions about what we've done? Yeah. Go, yeah, absolutely.
It's not a great question, but it's an important question to me. It's about streaming data analytics. Have you done any performance testing on your platform, and how does it stack up to the others?
Right, okay, so yeah, so the question is streaming data analytics, what do we do about streaming data, and what's our performance like? And so we're not trying to be like a real-time stock trading, streaming data analytics kinds of engine, but we're trying to deal with data streams and to do that performantly. And so for us, what that's about is our support for data feeds, which is you can sort of stream data into our system at high rates, sort of high defined by sort of data feed rates, not like microsecond, got to make this stock trade kinds of ways. We can deal with data streams, and we can run small queries over that data, or run larger queries over that data. That data is going into the system right now, and that data is available right now. And so we're much more kind of in the zone of regular databases than we are like the Hadoop zone, where the issue is, it takes a long time to initiate a job, and it's really designed only for batch computation. So our system is really aimed more at a range of use cases where that kind of batch computation, those large computations, we can do those, but we also have indexes. And that data that's sort of coming in those streams is being indexed as it's arriving. And now if you have a quick question, you're looking for the tweets in the last 2 minutes that have been about this topic, you can ask that question. We can exploit indexes to answer that. And so we're sort of closer to doing real-time-ish things. But we're not a real-time streaming engine. We're different than that.
So how does it stack in terms of performance to your...
So we haven't done any performance comparisons, and so I'm not sure how to give you sort of a meaningful answer, except to say that we're sort of in the milliseconds range when we're processing queries, or the hundreds of milliseconds range, as opposed to the seconds or hours range, which are more the size queries that you would target with something like a Hive or an engine like that. So if you're dealing with Hive, you're probably wanting to run queries that take at least minutes, if not hours, essentially. That's more the use case for those things. And we're designed for small queries as well as large. And so how we do that is because we index data, and we can answer small questions by looking at small amounts of your data. Whereas if you're dealing with this straight Hadoop stack, everything you ask turns into essentially a scan of all of your data. And I think MapR probably has some interesting technologies that they're building as well that we'll talk to them about. But that's kind of what we're doing technically about that. Other questions? Yes?
So if you have a customer that already has a lot of legacy data, some SQL, some raw data, so what would you recommend? How would you interoperate with the existing SQL?
Good question, yeah. So,
would you migrate some of the other stuff to yours? Or
right, so yeah, good question. So the real question here is like, what do you do about legacy data? And there's sort of two kinds of legacy data. There's like old legacy, which is sitting in relational databases. There's new legacy that is sort of sitting in files and sitting in Hive, essentially in HDFS. And so we're sort of working on that. So what we're doing right now is we have this external data set notion that I mentioned, where if you have file data or HDFS kinds of data, you can point us at that, and we will look at that as being an external data set. And you can run the same kinds of queries you could run over data that you put in our system over the data that's sitting in those files. So that's the good news. We can actually access your external data. Sort of the other good news is that if you wish your data were in our system because you want it to be indexed and you want to do a quick query, we can solve that problem as well. You can basically write a query that does a for over your existing data and selects the part of it that you care about and inserts that into one of our data sets, and then it will be parallelized and you can run queries. So you can sort of migrate data into our system from sort of new legacy data out of HDFS or files in that way. And we can run queries just over it where it is. The problem is that if it's in HDFS, we're kind of limited to the same thing that Hadoop is limited to today, which is that you have to sort of crawl over all the data to answer the question. And so we're also sort of working on, starting this summer, kind of another answer to the new legacy data problem, which is to make it possible to build indexes over data that we don't own. So today, all of our indexing technology, our secondary indexes, our B trees, our R trees, our text indexes, you can index our data, but you can't index if it's in an external data set. We will fix that. And so then we'll have even a stronger story for new legacy data. For old legacy data, relational, we're actually not working on that yet. We know that there's interesting stuff that we could look at to do there. We actually, the last of these OC hugs, sort of talked about how Microsoft is thinking about dealing with mixing new legacy and old legacy together. We're not doing that at this point in time. But we could look at doing that as well, potentially. But we're really right now sort of more after the semi-structured data world, and so our first kind of legacy data that we're trying to go after is the data that is in the new legacy, like Hive or Pig kinds of storage. Other questions? All right, so the team is here. Those of you wearing shirts, oh, sorry, was there a question? Are you pointing at someone who had a question? I saw an indirect reference to a question. Nope, okay. So the team is here. We'd be happy to sort of tell you more about the system, answer questions. We could even, I think there's one team member who's ready to maybe give a demo, we'll see. And so, if you'd like to see the system, sort of an application running, we can show you that as well. But we would encourage you strongly to go and download the system, give it a try, and if you're interested, talk to us more. We'd love to work with local companies. So, thanks.
Free shirts for both.
And, oh, yes, right, okay, so our shirt criteria. What we'll do actually, so Zach, who spoke up, will be the getter of shirts, and our shirts criteria is sort of the best question. So they'll have to huddle and decide what the best question was. Most useful tweets, and so we've been monitoring the Twitter stream, and we'll have to sort of summarize those answers. And then if you sign up on the AsterixDB user list, we'll take a look tomorrow and see who signed up, and we'll make sure you get shirts as well. So that's the plan. So Zach will take care of it, and we didn't bring them up because we want to size you appropriately. We'll give you the size that you need. And so talk to Zach to get your shirt. And he'll talk to you about your shirt. All right, that's our talk. Thanks.